the formula. And the distance, so this is number 9. And we have age of t, of course, is negative 4.9 t squared plus 24.5 t and plus 2. That's the correct descending order. And then they want the velocity after 2. Okay, so part A, velocity of 2 at 2 and 4. Part B, when max height, C, max height, D, hit the ground. So I don't have to go back to the book. That's it. And the velocity when it hits the ground. Okay, velocity at the ground. Okay, got it. Good. So we're asked first to find the velocity at 2 and the velocity at 4. What do I have to find first in order to find v of 2 and v of 4?
The derivative.
Yes. So v of t equals h prime of t. So we bring down, so this is negative 9.8 t plus 24.5. So in this function, I have to plug in 2 and I have to plug in 4. So what I highly recommend, put in the graphing calculator and determine them immediately. So negative 9.8 t plus 24.5. And then second and table. And I need to plug in 2 and 4. Whatever I get, I don't care. So 4.9. And this is, I think it was meters. Where is the function? Right, meters, seconds, and meters. Good, meter per second, good. So meter per second. And the other one, negative 14.7 meters per second, which means direction. Okay, now they're asking us to determine the maximum height. And this is a very important situation or question because it will come up in chapter 4, in the entire chapter 4. Okay, so let's talk about it. Now, I see that this is a quadratic function, and I know it has a maximum because the leading coefficient is negative. So if we wanted to graph this function, the function has to look like this. No question about it, because the leading coefficient is negative 4.9. So they're asking us when and also the maximum height. So they're asking us to find this point. In the past, in algebra pre-calculus, we would have found the vertex. Not anymore, because we have other tools now, more important tools than the vertex in algebra and pre-calculus. And I would like us to analyze something very important. So if I were to, at this point, draw the tangent line, and if at this point draw the tangent line, and if at this point draw the tangent line, and if at this point draw the tangent line, let's analyze what's happening here. What type of slope does this line have? Does this line have? Does this line have? In other words, I'm asking positive, 0, or negative.
Positive?
All positive, because the function is increasing. Good. Now if I do it, I repeat the process on this side. Tangent, tangent, tangent. What are the slopes of these lines, these tangent lines?
Negative.
Yes, because the function is decreasing. Now see, it's increasing and then decreasing. Obviously this is, we're going to call it later on, local or relative. They mean the same thing. We use them interchangeably, max. It doesn't matter if you prefer local max or relative max, is the same thing. So can anyone identify what is the slope of the tangent line at the local max?
0.
That's it. So there is gonna be a in-depth discussion in chapter 4 about this. Because see, if I have this situation, at this point, the slope is still 0, but there is no local max or min, because the function is always increasing. But if the function is increasing, has a slope 0, and there is another option, and then is decreasing, this must be a local max. So in order to determine what it is and when it happens, what we have to do is set the derivative equal to 0. When we set the derivative equal to 0, we will be able to identify this point. No longer needed the algebra that we know from a long time ago by finding the vertex. So here is our velocity. We're going to set it equal to 0, which means negative 9.8 t equals negative 24.5, and divide 24.5 by 9.8. 24.5 divided by 9.8. I didn't want to share the screen, so 2.5. So that is the time, 2.5 seconds. In other words, this is t equals 2.5 seconds. And this will be the max height. I have to plug in the function, I have to plug in 2.5 seconds to find the maximum height. So this will be h of 2.5. This is when? Well, t equals 2.5 seconds. How much? It's h of 2.5. So this was the derivative. I don't need the derivative right now. You can stay there patiently. I don't care. I have negative 4.9 t squared, and then plus 24.5 t, and plus 2. And all I want to plug in, and this is the second function in red, I want to plug in 2.5. So I get 32.625. So this is 32.625, and this is meters. Again, this will be a huge application in the next chapter, in which we're going to analyze the derivatives, first and second, and learn information from them, learn information about the function. So when all we have to do is set the velocity equal to 0 to get that, but when we are asked to find the maximum height, we have to plug it back in the function. When does it hit the ground? What does that mean? Hit the ground. When something hits the ground.
The height is 0.
Yes. Hit the ground means h of t equals 0. So I have negative 4.9 t squared plus 24.5 t and plus 2 equals 0. Yes, of course, at least I will eliminate the negative leading coefficient that I'm always allergic to. And then plug this in the graphing calculator. Under the apps. So we have apps, and we have this polynomial blah blah blah, number 9. It's second degree, but they call it order. That's fine. And the leading coefficient is 4.9. The next one is negative 24.5. And the next one is negative 2. And just give me the answer, please. So I will disregard the first one. Why? Why would I disregard? How dare I to disregard the first one?
Hold on, why are the signs
Time
flipped?
cannot negative.
Because time cannot be negative. So 5.08 seconds.
No, with the equation, why is 4.9 not negative?
I
Like, why
refuse.
are all the
I refuse to solve an equation with a negative leading coefficient.
Oh, so you did that. Okay, got it.
But that's my habit, because I may omit for some reason or make a mistake and forget that this is negative. I always eliminate the leading coefficient if it is negative, always.
Okay, thank you.
Do you have to? No. But it's very easy to, especially if you use the quadratic formula, for example. This is a problem because you have to put in the denominator. And if you use the calculator and not this feature, if you don't put parentheses in the denominator around that negative leading coefficient, you may not get what you're expecting. So we say that the shot or whatever it is, the particle, whatever we're discussing, it's not important. It hits the ground when 5.07 seconds from the moment of launching it. Now, we want to determine the velocity when it hits the ground. How do I determine that? How do I determine the velocity when it hits the ground?
Do you do V of
Exactly, of course. Yes. So that's why I'm happy that I have both functions in there. Now I'm looking for the first one. So I go to, see, this is the first one. And in this one, I have to punch in 5.08. So 5.08, and that's in the velocity. So negative 25, which means it's coming down, not going up. 284 feet per second. So in other words, because the velocity is negative, the slope of the tangent line is negative, the particle at 5.08 seconds is somewhere here, coming down. That's why the velocity is negative. The velocity will be positive, but now it's negative because it's coming down. Good. Any questions on this problem? Any questions on this problem? Any questions? Okay, we'll come back to other problems of these types. So let's start one of the most interesting, I would say. On page 11. So this is 3.9 called related grades. What does this mean? What is all about this? So this is a big topic. So imagine the following. I'm not a very good drawing in general, but if it's mathematical, I can, but if it's something abstract, not really. So imagine that this is a balloon and it has no air in it. Okay, so then I pump in some air, and then some more, and then some more, and then some more, and you got the idea. What happens when I pump air in a balloon? So assuming that the balloon is a sphere, Okay, so this is the radius 1. So here's the radius 2. Here's the radius 3. Obviously, this is bigger and bigger and bigger. Okay, then the volume 1, volume 2, volume 3. Of course, the volume of air here, and this one is bigger and this one is bigger. I'm going to say the surface area. Of course, this is smaller, this is bigger, this is bigger. So, as you see, something happens here. All these become functions of time. They're all functions of time. Because at time t1, I get this volume. At time t2, I get this volume. At time t3, I get this volume, and so on and so forth. So the volume depends on time. The surface area depends on time. The radius depends on time. The more I pump air into the balloon, the bigger the radius, the bigger the surface area, and the bigger the volume. So if I am talking about a sphere, let's say, the volume of a sphere is 4 pi over 3 r cubed. So the volume and the radius are connected by this relationship, are related by this relationship, by this equation. The volume is 4 pi over 3 r cubed. What happens is the rate of change of volume with respect to time will be related to the rate of change of radius with respect to time. Why? Because these two functions are related via this equation. Their rates of change, their derivatives, will also be related by an equation. Not this one, a different one. So that's why we call them related rates. This is related to this by a relationship. We're going to find it right now in a minute. So if two functions, in this case functions of time, are related by an equation, their rates of change will be also related somehow by some equation. So let's do that just now. So I'm going to put a dot under these two, reminding us that they are both functions of time. And I'm going to differentiate to find the relationship that relates their derivatives. So, can anyone tell us the rate of change of the left-hand side or the derivative? Oh, you're going to say dv over dt. On this side, can anyone differentiate? I have 4 pi over 3. Can anyone differentiate r to the third, keeping in mind that r is a function of t?
Would that be 3r squared times the
Yes,
derivative?
exactly. So I simplify, and we got the dv over dt equals 4 pi r squared dr over dt. So the two functions of time were related by this equation. Their rates of change are related by this equation. A totally different one, but related. What do you mean related? They are in a relationship. This is their relationship. That's what we mean by related rates. And you can say, okay, so what's this? Well, the problems will give us this to ask us to determine this. Or it will give us this to ask us to determine this. But we need to practice. There are many, many, many different situations. Any questions so far? This is nothing. This is just a preliminary. We didn't do anything. I just explained with a simple example how this works.